So now I want to talk about the heating curve. And hopefully you have had an experience where in the classroom or the laboratory where you have boiled water and taken temperature measurements at regular intervals and plotted the temperature versus time curve for that. It may have also just been a demonstration where I hooked up a computer with a temperature probe and put the probe in a beaker of water, of ice water, and then heated that water so that it went from ice water to boiling water. That would be the curve that would be generated would be a heating curve. Now I want to take some time, and I have annotated this graph with some vocabulary terms that you're going to be responsible for knowing. And it's one thing to write down the definitions of these terms and memorize them, but for me to really understand it, it helps me to show these terms on a graph. So again, I know this looks complicated, but let me try to help you understand that this is a graph of temperature versus time. So if we were heating up the water at time 0 and it was a solid block of ice, say, and we just got it out of our sub-zero freezer at a minus 20 degrees, and we took the temperature of it at time 0, that would be the temperature of it. And then if we slowly started to heat that block of ice up over time, it would eventually get to the point where it would start to melt. And then if we kept putting temperature or heat into the water, the substance, it would rise in temperature until it started to boil. And at that point, we would see some steam or some vapor come off the water until the water was all gone. It was steam, and if we kept on heating that steam, it would be super, super hot, and it would get hotter and hotter and hotter. So this is the whole process of heating the water from starting out being very cold, heating it until it's very, very hot. So when we were in class, maybe we only saw this portion of the curve, where we had a period of time where we had ice and water, liquid and solid water in the beaker. And until all of the ice melted, that temperature stayed the same, near 0 degrees Celsius. Then when all the ice melted, then the temperature of the water could increase until we started to get to another state change, until we got to changing from a liquid state to a gas state. As long as there was liquid and we were making gas, the temperature was going to stay at the boiling point, the boiling temperature, until all the liquid was gone, and then it started to shoot up again as really, really hot steam. Notice that the flat portions of these curves are happening when there's a change of state, when we're going from a solid to a liquid, or we're going from a liquid to a gas. What's happening here is that heat is going into the system and breaking the bonds that's keeping the particles together. When the particles are then free to move about more freely, then the temperature increases. So we're bringing all together all what we know about states of matter, kinetic theory. This is just a beautiful diagram that kind of pulls it all together. Boiling point is a temperature. It's different for different substances. So if you're looking at a graph, make sure you're not saying, oh, boiling point, that's 100, because the substance you're looking at may not be water. Boiling point for water is 100 degrees Celsius. Likewise, the melting point, ice melts at 0 degrees Celsius, but not all substances melt at that temperature. We like to use Celsius in science because 0 is where water freezes, 100 is where water boils. Makes a lot of sense to us. I don't know where they got Fahrenheit from. It seems kind of weird it would be 32 and 212. But Celsius is what standard we use for most of our laboratory measurements. Now there's a couple of other terms that you need to know. The heat of fusion and the heat of vaporization. I told you that this graph was a graph of temperature versus time. And I've got from 0 to 60 minutes, and that's when I did this experiment in the class period. We had about an hour to do this, so we tried to plot out this whole graph. But if you're putting energy in the system at a constant rate, then I could also call this x-axis a graph of an axis with energy, with units of energy. So if I was talking about time, we were talking about minutes. Or if I'm talking about energy, let's call it kilojoules. I don't know if we've talked about joules yet, but joules are a unit of energy. So this x-axis could either represent minutes or kilojoules. Now I bring that up because when we talk about the heat of fusion and the heat of vaporization, I'm talking about how much energy is required to melt the water, or how much energy is required to vaporize the liquid. We have to actually look at the difference between this point and say, well, all of the solid turned into liquid at 20 kilojoules, but it started melting over at 10 kilojoules. So 20 minus our final minus initial, 20 minus 10 is equal to 10. Our heat of fusion was 10 kilojoules for this particular amount of water. Likewise, we went from the liquid started turning into a gas at 40 kilojoules, and it was all gas at 55 kilojoules, so the final minus the initial, it took us 15 kilojoules of energy to turn all the liquid to gas. So that's an important difference. Pretty easy to look at the graph and say, oh, melting point is 0, boiling point is 100, but when you're talking about the heat of fusion or the heat of vaporization, you have to actually look at how many units of energy were put into the substance in order to cause it to have a complete state change. I hope that makes sense to you.